Follow the directions to respond to the following questions. There are two horizontal parts of this graph where temperature is not changing, but energy is being supplied to the substance at constant rate. Rate. Explain why does temperature not change at these stages? Answer. During the horizontal parts of the graph, the supplied heat energy is used to break the intermolecular forces rather than increasing the kinetic energy of particles. The first horizontal line shows melting, ice to liquid, and the second shows boiling, liquid gas. Therefore, temperature remains constant until the phase change is complete. Explain why the temperature and energy trends are not same for the same time intervals. Answer. Energy increases continuously because heat is supplied at a constant rate. However, temperature only increases when the substance is in a single phase, solid, liquid, or gas. During phase changes, the energy increases, but temperature remains constant since the energy is used to overcome bonding forces rather than raising temperature. A. What is the melting and boiling point of the substance? Answer. To find the melting and boiling points, you look for the flat, horizontal, parts of the temperature time graph. These flat regions show where temperature stays constant, even though heat is still being supplied. Why? Because during melting or boiling, all the heat energy goes into breaking bonds, not raising temperature. First horizontal line. Melting. As the temperature becomes constant at 50 degrees C for a short time. This flat region means the substance is changing from solid liquid. Asterisk during this time, temperature does not rise. Therefore, melting point equals minus 50 degrees Celsius. Second horizontal line. Boiling. Later in the graph, the temperature becomes constant again at 30 degrees C, and it stays flat for several minutes. This represents the substance changing from liquid gas. Again, temperature stays constant because heat is used for vaporization. Therefore, boiling point equals 30 degrees Celsius. How long does it take to melt completely, and how long does it take to vaporize from liquid state? Answer. From the graph. Time taken to melt completely equals 4 minutes, from 2 to 6 minutes. Time taken to vaporize completely equals 5 minutes, from 11 to 16 minutes. How much temperature increases in its liquid phase, X part of graph? Answer. From the graph. Temperature rises from 20 degrees Celsius to 80 degrees Celsius, so increase in temperature equals 60 degrees Celsius. Calculate latent heat of vaporization of the substance. Answer. Given data. Mass M equals 100 G equals 0.1 kilograms. Power of heater P equals 250 W. Time for vaporization T equals 5 minutes equals 300 S. Q equals P times T is equal to 250 times 300 equals 75,000 J. L equals Q slash M equals 75,000 slash 0.1 is equal to 750,000 J slash kg. Latent heat of vaporization equals 7.5 times 10 J slash kg. Final answers summary. 1A. Temperature constant because energy used for phase change, latent heat. 1B. Energy increases continuously, temperature only rises when not changing state. 2A. Melting point equals 0 degrees Celsius, boiling point equals 80 degrees Celsius. 2B. Melting time equals 2 minutes, vaporization time equals 10 minutes. 2C. Temperature rise equals 80 degrees Celsius. 2D. Latent heat of vaporization. L_V equals 1.5 / times 10 to the power of 6 / text J/kg.
Short response of the questions.
Why do dewdrops form on leaves and grass in a spring morning? Answer. Dewdrops form on leaves and grass on spring mornings due to condensation. Cool nighttime temperatures cause these surfaces to cool below the dew point, the temperature at which air becomes saturated. When this happens, water vapor in the air condenses into tiny liquid droplets on the cold surfaces. What is the effect of pressure and temperature variation on sublimation and deposition? Sublimation, solid gas. Answer. Increase in temperature, faster sublimation, more molecules escape solid. Decrease in pressure promotes sublimation, easier for molecules to leave solid. Deposition, gas, solid. Decrease in temperature favors deposition, gas loses energy to form solid. Increase in pressure encourages deposition, gas molecules force together. Why do vapors form on the handle and cylinder of a fire extinguisher when it is discharged? Answer. When a fire extinguisher is discharged, the gas inside expands rapidly, causing a sudden drop in temperature. This cooling causes water vapor in the air to condense into tiny droplets, forming vapors or frost on the handle and cylinder. How does sweating help to cool our body down during exercise? Answer. Sweating cools the body through evaporation. When sweat evaporates from our skin, it absorbs heat energy from our body, results in lowering our skin temperature. This process helps to cool our body temperature during exercise. Consider a piece of metal X initially at a temperature of 100 degrees Celsius. It is placed on a heater, which is providing heat at constant rate, until it reaches a final temperature of 400 degrees Celsius. The metal has a melting point of 250 degrees Celsius. A. Draw a temperature time graph illustrating the changes in temperature of metal X as it is heated. Answer. Temperature time graph for metal X. Melting point, 250 degrees Celsius. Solid phase heating, 100 to 250 degrees Celsius. Temperature rises linearly with time as heat is absorbed. Slope depends on the specific heat capacity of the metal. Melting phase, 250 degrees Celsius. Temperature stays constant at 250 degrees Celsius until all solid melts. Heat absorbed is used to overcome latent heat of fusion, no temperature change. Liquid phase heating, 250 degrees Celsius, 400 degrees Celsius. Temperature rises again nearly once melting is complete. B. Now, examine a different metal, Y, which has a higher latent heat of fusion compared to metal X. Both metals have identical melting points and heat capacities. The heating procedure for metal Y is conducted under the same energy supply rate as metal X. Describe how the temperature time graph for metal Y will differ from that of metal X, considering the implications of its greater latent heat of fusion. Answer. Comparison with metal Y. Higher latent heat of fusion. Metal Y requires more energy to melt, higher latent heat, but has the same melting point, 250 degrees Celsius, and heat capacity as X. Effect on the graph. Solid and liquid heating phases, identical slopes, same heat capacity. Melting plateau, 250 degrees Celsius, takes more time to melt fully at the same heating rate. Graph shows a wider flat region at 250 degrees Celsius. How does the pressure in a car tire change during a long drive on a hot day? Answer. During a long drive on a hot day, the air inside the car tire heats up, causing the air molecules to move faster. This increases the pressure inside the tire because pressure is directly proportional to temperature. How does understanding thermal expansion help prevent cracks in sidewalks during hot weather? Answer. Understanding thermal expansion helps prevent sidewalk cracks by expansion joints. Gaps between concrete slabs allow space to expand in heat. Material choice. Using concrete with lower thermal expansion coefficients reduces stress. Reinforcement. Steel bars, rebar, control cracking by managing expansion forces. Imagine you are stuck in the snow with your car. Which would be more effective for melting the snow trapped underneath, a pot of hot water or a high-powered heat lamp? Answer: a high-powered heat lamp is more effective because hot water cools quickly and may refreeze, worsening the problem. The heat lamp provides sustained, directed warmth to melt snow without adding moisture that could turn to ice. It avoids the risk of thermal shock, cracking cold components with sudden heat. How does the evaporation of water from a plant's leaves help to transport water and nutrients throughout the plant? Answer: evaporation from leaves, transpiration, creates negative pressure in the plant's xylem, pulling water and dissolved nutrients upward from the roots like a straw. This transpiration pull relies on cohesion, water molecules sticking together. Adhesion, water clinging to xylem walls. Why does adding ice to a drink cool it down more effectively than adding cold water? Answer: adding ice cools a drink more effectively than cold water because ice absorbs extra heat as it melts, latent heat of fusion, removing more energy from the drink than cold water, which only lowers temperature by conduction. What are the challenges associated with maintaining the extremely low temperatures required for superconductivity to occur? Answer: maintaining the extremely low temperatures needed for superconductivity is challenging due to the high cost, complexity, and energy consumption of cooling systems, like liquid helium. These systems must keep materials stable and isolated from external heat. Long questions answers/response. Define latent heat. Differentiate between latent heat and specific latent heat of fusion. Write their formulae. Answer: definition. Latent heat is the amount of heat energy required to change the state of a substance without changing its temperature. Latent heat. Specific latent heat of fusion. Total heat energy required to change the state of a given mass of a substance. Heat energy required to change the state of unit mass of a substance from solid to liquid without change in temperature. Depends on mass of the substance. Independent of mass, it's a property of the material. Formula: Q equals ml. Formula: Li equals Q/m. Unit: joule, J. Unit: joule per kilogram, J/kg. Differentiate between latent heat of vaporization and specific heat of vaporization. Give their formulae and units. Answer: aspect. Latent heat of vaporization. Specific latent heat of vaporization. Definition: total heat energy required to convert a given mass of a liquid into vapor at constant temperature. Heat energy required to convert unit mass of a liquid into vapor at constant temperature. Depends on mass. Yes. No. Symbol: Q. LV. Formula: Q equals mLV. LV equals Q/m. Units: joule, /
Joule per kilogram, kilogram.
What is evaporation? Differentiate between boiling and evaporation. On what factors evaporation depends? Answer: evaporation. Evaporation is the process by which a liquid changes into vapor from its surface at any temperature below its boiling point. It is a gradual process and occurs naturally, even without boiling. Feature: evaporation. Boiling. Where it occurs: only at the surface of the liquid. Throughout the entire liquid. Temperature: occurs at any temperature. Occurs at a specific boiling point. Speed: slow and natural process. Fast and vigorous process. Heat source needed? May occur without heating. Requires continuous heating. Bubble formation. No bubbles form. Bubbles form and rise to surface. Factors affecting evaporation. Temperature. Temperature, kinetic energy evaporation. Surface area. Surface area, more particles can escape evaporation. Humidity of surrounding air. Humidity evaporation. Wind speed. Wind speed removes vapor layer evaporation. Nature of liquid. Volatile liquids, e.g., alcohol, petrol, evaporate faster than water. What are linear and volume thermal expansion of solids? Discuss qualitatively the factors upon which these thermal expansions depend. Answer. When solids are heated, they expand due to the increase in the average separation between their atoms. This expansion can occur in length, area, or volume. Two common types are linear thermal expansion. Linear expansion is the increase in length of a solid when its temperature is increased. Formula: delta L equals LUT. 1. Volume thermal expansion. Volume expansion is the increase in volume of a solid when its temperature is increased. Formula: delta V equals VOT. Factors affecting thermal expansion. Factor. Effect. Material type. Different materials have different expansion coefficients, e.g., metals expand more than ceramics. Temperature change at greater temperature increase more expansion. Original size. Large initial length or volume, greater absolute expansion. Atomic structure. Materials with looser atomic bonding tend to expand more. What are the uses of thermal expansion in our daily life? Give examples. Answer. Thermal expansion is not just a scientific concept, it has many practical applications in our daily life. Engineers and designers use this knowledge to create safe and functional structures and devices. Use/application. Explanation/example. I. Gaps in railway tracks. Small gaps are left between sections of railway tracks to allow for expansion in hot weather and avoid buckling. 2. Expansion joints in bridges and roads. Bridges and concrete roads have expansion joints to allow for expansion and prevent cracking or warping. Metal lids on glass jars. Heating the metal lid causes it to expand, making it easier to open, e.g., by placing under hot water. 4. Bimetallic strips in thermostats. Used in electrical devices where two metals expand differently to break or make circuits, e.g., in irons, heaters. V. Overhead power lines. These are hung loosely so they don't break when they contract in winter due to cooling.
6.
Riveting in metalwork. Hot rivets are used to join metal parts. As they cool, they 3. Contract and hold the parts tightly together. 7. Hot air balloons. Heated air expands inside the balloon, reducing its density and causing it to rise. 8. Fitting of wheels on axles. Metal wheels are heated to expand, then fitted onto axles. As they cool, they contract and grip tightly. Explain thermal expansion of liquids in detail. Answer. Thermal expansion in liquids. Liquids expand when heated and contract when cooled, but unlike solids, they do not have a fixed shape. Their expansion is greater than solids because the intermolecular forces in liquids are weaker, allowing molecules to move more freely. Thermal expansion in liquids is measured in terms of volume expansion, since liquids take the shape of their container. There are two types of volume expansion in liquids. Real volume expansion. Apparent volume expansion. Real volume expansion, the actual increase in the volume of the liquid itself due to the rise in temperature, regardless of the container. Generally, this expansion is similar to volume thermal expansion of solids. We can use the same formula for coefficient of real volume expansion of liquids urate as we do for solids. It is defined as fractional increase in real volume of the liquid for 1 Kelvin rise in temperature. Y equals beta.
Y rovno V lomka vod.
Apparent volume expansion, the observed increase in volume of the liquid as seen in the container, considering that the container itself also expands when heated. When both the liquid and the container expand, the container's volume also increases. So, the expansion observed is less than the actual expansion of the liquid because the container grows too. Thus, the apparent expansion equals real expansion of liquid, expansion of container. Y apparent equals Y real, Y expansion. The coefficient of apparent expansion of liquid Y alpha is defined as a fractional increase in apparent volume of the liquid for 1 Kelvin rise in temperature.
Y rovno V lomka vod.
Discuss application of bimetallic strips in temperature control devices like thermostats. Explain the principle of thermal expansion that allows the bimetallic strip to function, and illustrate how the differing expansion rates of the two metals are utilized in practical. Answer: bimetallic strips. A bimetallic strip consists of two different metals, e.g., brass and iron or copper and steel, bonded together along their lengths. These metals have different coefficients of thermal expansion, meaning they expand at different rates when heated. Principle used: when heated, each metal expands, but one expands more than the other. Since the metals are bonded together, the strip bends or curves toward the metal that expands less. This bending is predictable and repeatable, making it useful for mechanical switching based on temperature. Working of bimetallic strip in a thermostat. At normal temperature, the strip remains straight and the thermostat circuit remains open or closed as designed. When temperature rises, the metal with a higher expansion coefficient expands more. The strip bends. This opens or closes an electrical contact. When temperature falls, the strip returns to its original shape, reversing the contact status.